Hi students, today I am going to explain one problem from chapter 6, which is the chapter 6 is about 2 raised to k design. So before we talk about the problem, let us talk in general about chapter 6. What is 2 raised to k design? I am sure most of you know about it. K represents the number of factors, how many factors are there in the experiment, that is represented by k, and number 2 that represents the levels each factor has. So chapter 6 talks about only those experiments in which each factor has only 2 levels. So if we are, let's say, if in an experiment we have 2 factors, pressure and temperature, and we are using only 2 levels of pressure. So we are running that experiment at, let's say, 10 and 20 units of pressure. So 10 and 20, these are only 2 levels we are using for pressure. And similarly, let's say temperature, we are running the experiments at the level 10 degree Kelvin and 30 degree Kelvin. So 10 and 30, these are 2 levels that we are using for temperature. So you can see in this 2 factor experiment, we are using only 2 levels for each factor. So this is 2 raised to 2 type of design, right? And in such designs, the low level is represented by negative sign and high level is represented by positive sign. Or sometimes they use -1 and +1 to show the low level of the factor and high level of the factor. Right now, let's talk about this problem here. I will read this problem first. Nickel titanium alloy is used to make components for jet turbine aircraft engines. Cracking is potentially serious problem in the final part, as it can lead to non-recoverable failure. A test is run at the parts producer to determine the effects of 4 factors on cracks. The 4 factors are powering temperature, titanium content, heat treatment method, and the amount of grain refiner used. 2 replicates of a 2 raised to 4 design are run, and the data is shown in this table here. Now, some important thing about this problem is, as I was reading this problem, you may have noticed that there are 4 factors in this experiment. First one is factor A, which is powering temperature. Second is factor B, titanium content. Third, heat treatment method, factor C, and the amount of grain refiner used, factor D. So 4 factor, and each factor has only 2 levels. So that means this is a 2 raised to 4 design. Right now, we don't know, in the problem they didn't mention what are these 2 levels, but there is a low level and there is a high level for each factor. And the response variable is length of crack in micromillimeter. That is the response variable, right? And we want to study the effect of these 4 factors and the interaction between them on our response variable. Now there are 2 replicates, correct? That means we will run the experiment, like we will run 2 experiments at each combination of factor levels. So if let's say we have only 1 replicate, then that means we are running the experiment only once at each combination of the factor levels, right? Then 2 raised to 4. So in that case, there will be total number of 16 experiments. But since we are using 2 replicates, we are repeating the whole set of experiment twice. So we will have a total number of 32 trials, right? So you can see in this table there are 16 rows plus the replicate 1. You have values of the response variable, the length of crack, I imagine, for replicate 1, and for replicate 2, that means 16 readings, and then these 16 readings. So 32 total readings we have. Also, it is very important to understand this table before we try to solve the problem. Now let's see, first 4 columns we have given A, B, C, D, 4 factors, and you can see here negative and positive signs are there. So negative sign representing the low level of factor A, and positive sign will indicate the high level of factor A, and similarly for other factors as well, right? Now let's concentrate on the first row. So we have 4 negative signs. That means this particular trial we are running at low levels of all the 4 factors, right? Now this particular column, treatment combination, you can see that each particular each particular combination of factor levels is represented by a unique letters here. For example, low levels for all the factors is represented by this one in the bracket. Then next row we have high level of factor A, which is indicated by positive sign, and low levels of remaining 3 factors. This treatment combination is represented by small a, right? And you have notations for all the other combinations, and we also have the results of the response variable for each trial. Now sometimes in some of the problems you will not be given these 4 columns, you will be only given these notations, and from those notations you will know, you can find out what because this particular letter indicates a unique combination, right? So if you have only this letter, you should be able to tell what, like, the 4 factors, which levels were used for this particular trial, right? So example, if only letter B is given to you, then you should be able to tell that A is the A, C and D, these 3 factors, low levels are used, but for factor B high level is used, right? Like you can see here, for example, the A, whichever factor is at high level, we are representing that factor by small letter A. So A, we have a high level of A, we used small a to represent this particular combination. Similarly here we have a high level of B, so we used small b, and similarly you can see A, B, C here. So that means A, factor B and factor C, these 3 factors we are using high levels of these 3 factors. So now you get this point, right? Also there are tables in the book, and these tables show what basically, like these tables show the these combinations of negative signs and positive signs and related like notations. Now the one more thing I would like to emphasize at this point of time is it is extremely important that you enter the data correctly in Minitab, particularly for chapter 6, because at least 9 out of 10 times you may end up entering data incorrectly. So please pay attention when I enter this data in Minitab. Right now I will 16 rows. Now we need to enter the data, this data in Minitab, right? And this is a little different than what we used to do previously. I am going to click on Stat, and we always choose this ANOVA option here, right? We studied one-way ANOVA problem in which there was only one factor. We studied we used two-way option where we use this for randomized block designs. Then in which there is a one factor in reality, but there is another factor which is a block. To avoid any variations, we use blocks, right? And then we also used the balanced ANOVA option, where there were more than one factor, and we wanted to study the effects of factors and the interaction among the factors on the response variable, right? So we studied all that. But now for chapter 6, for 2 raised to k design, it's a little different. I will click on stat again, but rather than choosing ANOVA option, I'm gonna choose DOE option this time, and then I'm gonna click on Factorial Design. Factorial, right? Next is create Factorial Design. So I'm going to create Factorial Design, and you can see here the 2-level factorial. Yes, our design is 2-level because we have 2 levels of each factor, that is 2 raised to 4 design. So 2-level, that is good. Number of factors, how many factors we have? We have 4 factors, A, B, C, D. So I'm gonna select 4 here, right? Next I will click on designs, and we don't want half fraction, we want full factorial, 16 runs, right? So I clicked on full factorial. Also the number of replicates, you can see here number of replicates. How many replicates we have? We have 2 replicates. So I'm gonna click on that, and we don't have any blocks, so number of block is 1. Now I say okay. Next is I'm gonna go to option, and there is something called randomize runs. So I'm gonna unclick it because I don't want to randomize runs. Why? Because I just need to enter the data in this format. It is, the runs are already given here, which is like a systematically organized, they are not randomized. So I want Minitab to generate the design in the same format. Otherwise it will be difficult for me to match these values with the combinations that Minitab will give me. So that's why I'm clicked randomize runs, and I'm gonna click OK. Now results, there's nothing, it's all okay. Factors, now see here we have A, B, C, D. We can change the names, we can give the names to each factor, but I'm gonna keep it as it is. Then I can select the type of each factor. I'm gonna keep it numeric, doesn't matter. And you can see in Minitab, -1 is used to show the low level of factor 1, and +1 is used to show the high level of factor, and 4 factors we can see here, so that's fine. And I'm gonna click OK. Now you can see here the Minitab has created the factorial design for us. Ignore the first 4 columns, concentrate on these 4 columns. We have A, B, C, D, 4 factors, and we have a combination here, -1, -1, -1, -1 means the low level of all the factors, right? These are the combinations. Similarly here, +1, -1, -1, and -1, so high level of factor A, and low level of remaining 3 factors. So this is basically representing this particular design A, right? And I believe that this sequence here is same as this sequence here, but when you enter the data in Minitab, please make sure that the sequence is same. If the sequence is different, then it doesn't matter, but you have to match when you enter this particular reading, you have to match this combination with the combination here, and then you have to enter the reading in front of that, right? Otherwise the whole idea of entering the data correctly, that will not work. You have to make sure that your values are matching up to the right combination of factor levels. So good, we have all the, see now we have 16 particular experiments. This is our replicate 1 basically, and for 16 of them, right? Now this is replicate 1, and you can see on the 17th row again we have -1, -1, -1, -1. That means this is our second replicate, the same sequence of factor level combinations. So we have 2 replicates. Now here I will put the response variable, right? Now we have everything, but we don't have the values of response variable, and I will copy the readings from here into the Minitab. So let me copy all these 16 rows. Similarly, what I will do is copy the second column and post it here. So now we have all that is needed. We have all the factor level combinations, and we correctly entered the respective values for the response variable here, right? Now next thing is to analyze this experiment. So all the experimental readings are recorded in Minitab. Now to analyze the experiment, again I am going to go to DOE, then Factorial, and then I am going to do the analyze Factorial Design, right? I'm going to click that. Let's go back to the problem here, and now let's look at what we need to do. For example, here it says estimate the factor effects, which factors appear to be large, right? Next is conduct an analysis of variance, do any of the factor affects cracking, and we will do that as alpha value of 0.05. Then it says write down a regression model that can be used to predict crack length as a function of the significant main effects and interaction you have identified in part B. Then we need to analyze the residuals from this experiment. As we always do, we analyze the residuals. Then is there any indication that any of the factor affects the variability in cracking? Okay. And finally, what recommendations would you make regarding process operations, right? And we need to use interaction and our main effect plots to assist in drawing conclusions. So good. Basically, we need to analyze this experiment and make a recommendation. Like first we need to find out which factors are affecting the crack, and which interactions are affecting the crack. Then next is we need to analyze the residuals to make sure that the assumptions behind these models are appropriate. And finally we need to make recommendations regarding what particular values of 3 factors, what particular levels of these 4 factors basically should be used for the optimal process, right? So coming back to Minitab here, again we'll go to stat, DOE, Factorial, and then we need to analyze this design. So right here in response I'm going to select column C9, which is our response here. Next is we'll look at terms of this particular model. All terms are good. We are using default and factor A, B, C, D, and then the interaction AB, interaction between A and C, interaction between A and D. Similarly, the interaction between A, B and C, and like other you can see, and finally the 4-way interaction between factor A, B, C and D. So all elements are included in this model. So I'm going to click OK. Then covariates, that is nothing to enter there. Graphs, again graphs, we're gonna use 4-in-1 plot to get all these things covered up, but basically we are mainly interested in the normality plot and the residual versus fits, residual versus predicted values. These two graphs we are mainly interested in, but anyway I'm going to select 4-in-1, and again we can plot the residual versus variables. I can plot residuals versus A, factor B, factor C, and factor D, right? And you can see alpha value of 0.05, which we already have there, and I will click OK, and then I'm gonna hit OK button to see what is our result, right? Okay, so I have all the graphs and I have all the relevant information. So let's first look at the table, ANOVA table that we get. So we can see this is the table that we should be looking at. You can see here this table. So if we look at this table here, we will see that we have first column, we have effect, the values for the effect that answers our first question here, estimate the factor effects, and this is the estimated effects in the first column. Next it says the question is conduct an analysis of variance and do any of the factors affect cracking. So that also, if we look at this table and these p values, it will tell us which factors are significant, which factor are affecting the response variable. Now look at the factor A here, p value is 0, right? That means this factor is significant. P value is less than alpha value. This factor is significant. Similarly, factors A, B, C, D, all of them are significant because p value is less, and also interaction between A and B, interaction between A and C, these two interactions are also significant. They have significant effect on the output or the response variable. Next few interactions you can see here, p value is higher than alpha, so the interaction between A and D is not significant, and same is true about all these three interactions. Now the three-way interaction between A, B and C seems to be significant because we have p value 0, which is less than alpha, and remaining all other interactions are not significant, p value is higher, right? So that answers the second question. Now third question is write down a regression model that can be used to predict crack length as a function of the significant mean effects. So we need to write a regression model, right? And that regression model is also here. If you see, we have the coefficients of each factor. So we have coefficient of factor A is 1.509. So this is second column, which shows coefficient. That is the answer for the part C. Only thing that I need to add in order to find the answer for the regression model, given in this table, as I said, the coefficients of the factors are given, but when you write the regression model, you need to ignore the factors or the interactions that were not significant, right? So the regression model in this case would be 1.509 multiplied by factor A, 1.988 multiplied by plus factor B, right? All these factors A, B, which were significant, and their coefficients, that forms your regression model. Now let's look. Now we'll study this table. Now let's look at the graphs that we have. So first graph I am going to look at is the normal probability plot. So you can see here I don't see any I don't see any abnormality in this plot. The normality assumption seems to be good. So normality plot is good. Similarly, if you look at the residuals versus the fitted value, there is nothing unusual about this plot either, right? So that is good. So our assumptions behind these models are okay. Now let's look at the other plots. Doesn't seem anything unusual about these plots also. These are basically plots of residuals versus the factor, right? So nothing unusual about these plots. Now one last thing that we need to do. So what did we do? We created the design, we entered the values of the response variable, and then we analyzed the design. So we analyzed all the factors and their interactions, and we found out which factors are significant. We also analyzed the effects. We found out the regression model based on these coefficients, and we also checked all the graphs to make sure that the various assumptions behind these models are appropriate. Now next thing we need to do is what recommendations would you make regarding process operations, right? So we need to make recommendations. So there are many ways to do that, but what I will do is I will basically go to again stat and go to design of experiments, factorial, and see I can plot factorial plots, right? So I'm going to select this. I can plot main effects plot I can make, then I can create interaction plots, and I can also create cube plots. So basically I will select cube plot. I can plot all of them, and all of them give me a very good picture of the process, but this time I will focus only on cube plot. And then we need to go to setup, right? First cube plot, cube plot means plot a three-dimensional graph on which we can use three variables, three factors at a time. So first cube plot I will use factor A, factor B, and factor C, and I will hit OK, and here is my cube plot, right? Which is A on x-axis, B on y-axis, and C on g-axis. Similarly, I will again go back to stat, DOE, factorial, and factorial plots, again cube plot, but this time I will take C back and I will add D to the plot. Sorry, C I need to take back, ABD, right? And again OK, and I'm going to click OK. One thing that I didn't do is, well, I need to go back because we need the value output, the values of the response variable on these different points. So I will plot this again. Go to stat, DOE, factorial plots, right? Cube plot, then setup, and here responses, right? Which we need to select responses. And first I will plot a graph of A, B, and C. Here we are. So now this time, as you can see, we have values of response variable at each point. Now again I will go to stat, DOE, factorial plots. Only difference is this time I am going to select D and take out C. So I have two cube plots. Now let's study these two plots here. So I'm looking at first cube, which is A, B, and C, right? Now look at these, all the values these are crack lengths, and crack length is problematic. We don't want cracks, so that means low values are good, right? Low value of crack length are better. So I'm going to look at all these values on this cube and see which is at which point I have lowest value. So right here you can see 5.1238. this value seems to be the lowest value on this cube plot, and this value at this value, if you look at this point, we have factor A at +1, that means high level of factor A. C, you can see C1, a +1 here, so high level of factor A and factor C, but B is on vertical axis, and at this point B is -1, that means low level of factor B. So from this cube we can say that the optimal positions are A and C at high level and B at low level. Now again, if we look at the second plot, now we know A, B, C, the optimal levels. For D, again I am going to look at all these values and find out the lowest value, which is 8.4917, right? But that is not good, because we said that we are going to use high value of factor A based on the other cube here, right? So here I will stick with that, and it's kind of little contradictory, but I'm gonna stick with that because you can see 7.7313 and 5.1238. this value 5.1238 is less than 8.4917, right? So I'm gonna stick with high value of A, and now D is basically, so this is the next lowest value, which is 9.598, and at this value D is -1, which is the low value of D. So from these two cube plots I can say that factor A and C should be at high level and factor B and D should be at low level. Also I can, like as I said before, we can plot more graphs to get more understanding of this, all the factors and the response variable at each of these factors, or at each of the interactions. But I think for now these two plots that I already have here, they are sufficient for me to make conclusions, right? So that is all about this particular problem. So what you need to do is, particularly the most important thing is to create the design correctly and to enter the data correctly in the Minitab. This is the major task. Once you do this job correctly, then rest of the problem is very easy to solve. There is nothing, you just go to DOE and do factorial analysis and plot some graphs and make conclusions based on the graphs and the ANOVA table that you get, right? So I think now you are in a good position to do your last homework. And one more thing is, there will be definitely a problem of 2⁻k design on your final exam. So it is very important that you understand this problem correctly and do final homework carefully. Thanks. Bye.